Okay. Again, I uploaded the videos also, whatever you have not received in the MS stream, even 29th, and then yesterday's again I uploaded in the stream. If you want, you can go through that.
Thank you,
Okay.
sir.
So fifth module, that is bolted joints and riveted joints. First, we'll see the bolted joints and then we'll see the riveted joints. Now, you know the bolted joint means nut and bolt for fastening the two parts. So generally in the temporary assembly, so the temporary assembly means whenever we require to, I'll stop the recording once again, 1 minute. Yeah. So bolt and nut, this wherever there is a nut and bolt, we always say that is a temporary joint. Again, it is this bolted joint, then riveted joint and welted joint. These are the three joints. We use this for joining the two parts, two different parts. So you know the welded joint, it is the permanent joint, right? Once you weld the two different part, then it is difficult to remove. Definitely we can remove that two part, we can separate that two part, but it will get damaged, right? And again, we have to, if you want to again assemble it, you have to rework it and then only we can assemble that. So that's why that joint is called the permanent joint. Then if you see the riveted joint, you must have seen sometimes we use the rivets. Now, if you want to remove that or if you want to dismantle it, then you have to break the rivet. And rivet is it is a very small part, but it will not damage the two parts which you are joining, right? Only the rivet will get damaged and you have to replace that rivet with new one if you want to again assemble it. Okay. Whereas, and that's why that is called the semi-permanent joint. And the third one, where we use the nut and bolt, it is purely a temporary joint because we can easily remove that. Whenever you require to disassemble it, you just unscrew the, sorry, you remove the nut and remove the bolt. Definitely you can separate out the two different parts. And suppose you want to join that, again insert the bolt and then tighten the nut, you will get the joint. So it is purely a temporary joint. Now, in the bolted joint, always we know we use the nut and the bolt. Now, whenever we are designing this bolted joint, that means you have to design the bolt. Now, design the bolt means what? Design of bolt means you have to decide the core diameter of the bolt, and on the basis of that core diameter, you have to decide the nominal diameter of the bolt. Okay, because these bolts are readily available in the market. If you go to the market and if you ask, give me the M10 bolt or M12 bolt, then that shopkeeper definitely will be able to give that bolt. So which bolt you want, what you which bolt means what is the size of that bolt, whether it is 16 m or 12 m or 10 m. Now this m represents the nominal diameter. Nominal diameter means what? If you remember, I don't know whether in first year you studied the thread profiles of the screw and all, but even if you have not studied, then generally, if suppose this is the cylindrical part and on which I'm making here the threads, right? And these threads we are representing like this. Okay, so actual threads looks like this, right? This one. I have taken here this small part of the threads. Now you can see there are, if I again enlarge like this, this is the thread profile. So this is the peak part, okay, and this one is the crest. So generally, this thread profile is something like this, the smooth one. Now whatever the peak part you can see here, suppose this is the outer part and this one is the center line. So from here, this is the radius, right? I have taken here this portion only, okay, small portion. So from here to here, initial diameter of the cylindrical rod is this one. And then see at the root here, this diameter is definitely less than this. And for this diameter only, we are showing here this line. Generally, the thread representation in the drawing, we show here the double line. Up to here, suppose this is the threaded portion and then it is cylindrical portion. So these two lines represent this inner two lines. This is the core diameter and this one is the outer diameter, right? And always the chances of the failure of this thread give me 2 seconds. I will draw here. This type of threads. So always what will happen, the chances of failure, it is along the core diameter. See here from this to this is the minimum diameter, okay, and this minimum diameter we represent and we call it as a core diameter. So core diameter or minimum diameter. So always, generally you must have heard the slip of the thread. Sometimes this happened. We say that the slipping of the thread means what? Here either the threads of the nut or threads of the bolt get sheared off and shearing is occurring here. Okay, so that's why that gate fails. So how much the tightening force you are applying over the nut that will decide how much the shear stress will develop here. See here in this diagram, if you see, these are the two different parts. Suppose we are joining here, right, with the help of this bolt. See this one is the bolt, right, where the core diameter is DC and this outer diameter is D, or you can say the nominal diameter. But here you can see this threaded portion. Now this portion, it is coming out. Then this one is the nut. Okay, and this is so threaded portion here with this nut and bolt. These are in contact, and this one is the height. We'll see why that nut height is important. That will derive here. Now, here always either the failure of this nut, it is due to the shearing of the threads, and another one is the tensile stress. See, when we tied the nut, when you are using here, suppose a spanner for tightening the nut, what is happening? This nut will try to move downwards and this bolt will try to move upwards, right? So which type of stresses develop here in this bolt? Here in this bolt, the tensile stress will develop, right? Here in this whole body. And if you consider this only the threads, here the shear stress develop. Okay, so as there is a tensile stress as well as the shear stress, the material generally we use for the bolt, it is again the plain. Yeah. Someone wants to say something? Okay. So because of this tensile and the shear stress, we use the material for the bolt, it is plain carbon steel. It may be 40C8, 45C8, or sometimes we use where we want very high strength. At that time, we use the alloy steel, that is 35 mm, 6 mo. Okay. So as I told you, this bolted joint is subjected to tensile force, right? When we are tightening it. And the cross section of the threaded portion, that is only the weakest portion. Why it is so? Because in the threaded portion, as I told you, this is the minimum diameter, right? Which is core diameter. So definitely, wherever there is a minimum cross-sectional area, see, if it is only cylindrical part, inside view you can see the circle, right? Now there is a threaded portion, so definitely it is inside. So wherever there is a root, if I take a section, you will get this diameter, which is less than the D. And this diameter, this is the core diameter. Now, if this core diameter is less than the actual diameter, that definitely this area, it is less, right? So this area, it is pi by 4 and diameter is DC, so pi by 4 DC square. Correct? So this is the weakest area where the failure can occur. It is again due to the tensile, because here wherever there is no threaded portion, here definitely the cross-sectional area is more because this diameter is more. This is D, right? This area is more. So this bolt will not fail here. The bolt will fail always at the weakest section, and that weakest section is pi by 4 DC square. And therefore, see the tensile stress, it is always equal to the force divided by the cross-sectional area. Correct? So force, it is P. Suppose tensile force is P. And the cross-sectional area, it is pi by 4 dc square. Right. Now, suppose this is for the tensile stress. Now, if I consider here this height of the nut, if it is h, and I will assume that the failure occurs in the thread of the bolt and not in the nut. See, whenever we are using nut and bolt, always in the nut there is the internal threads and in the bolt it is the external threads, and both the threads are in contact. Okay, here we are assuming that the whatever the failure of the threads, it is only, we are assuming here, right? This is our assumption. I'm not saying that it will fail only for the bolt, right? But we are assuming that the failure occur only in the threads of the bolt and not in the nut. Now, if this is our assumption, for this, what should be the height of the nut? That nut should not get failed. That we'll see. Now, again here, we know that the tensile stress, it is equal to this sigma yt divided by FOS. Okay, so now we know that the load, tensile load, it is equal to, as we have written, sigma t, it is equal to P divided by area. So from this we can write P, it is equal to area into sigma t, and area is pi by 4 dc square, and sigma t is what? Sigma t is sigma ut divided by FOS, right? Sigma ut or SYT, sorry, not ut, yt, yield stress, not ultimate stress, yield stress. So this SYT or FOS. Now, we know this is one equation. Okay, this is for the tensile stress. We say here this is equation A. Now another type of failure, it is the shear failure, and as I told you, the shear failure occur, it is always in the threads, correct? So wherever there is a threads, the shear failure will occur. Okay, like this. So these are the threads. So where the failure will occur? Here at the core diameter. Now, if I assume that my nut is here, okay, and the height of nut, this is my h. Now, in this height h, there must be the n number of threads, correct? From here to here, this height h. Now, this whole should get sheared off, whatever it is. I have shown here 2 threads, but there may be 1.5 or 2.5 or 3. That depends on the pitch, right? If you know, the pitch means this distance. Okay. If pitch is small, number of threads will be more. If the pitch is large, number of threads will be less for this height, correct? But one thing is fixed, that if this is BC and if the shearing is occurred, shearing will occur something like this along this area. Okay, along this one. Now, can you tell me this area is how much? This area, it is equal to the circumference of this circle into this height, right? And this height, it is equal to the height of the nut, and circumference of this circle, this core diameter, right? This is DC. Diameter is DC. Circumference is how much? Pi into DC. So pi into DC, this is the circumference, right? Into this height, this is the shear area. Shearing will occur here. You understood this? Shearing is occurring here along the DC, right? So these threads are along the circumference. Okay? These threads are along the circumference. It is like this. If it start from here, it will go something like this. Then it will again comes back. Again, it will move like this. So again, so this type of threads are there, right? So it is along the circumference. So the circumference of the circle into h, that is the shearing area. Now, this shearing area into the shear stresses, it is equal to the strength of the bolt, right? And strength of the bolt means whatever the load is acting. So that load is P. So P is equal to area into the shear stress. Area is pi DC into H. And shear stress, see, now don't get confused here. It is otherwise I'll write this sigma T only. This is sigma pi T. Okay. So how we calculate this sigma T? Sigma T yield stresses divided by the factor of safety. Correct? And tau shear stresses. Shear stress is 0.5 times sigma YT divided by factor of safety, or this sigma T. Correct? So that is only written over here. See, P it is equal to pi into DC into H. Suppose this is sigma YT divided by 2. That means whatever this is written here, this is what? This is tau, shear stress. Correct? This is divided by 2. 1 divided by 2 means 0.5. Correct? So you are getting one more equation. P it is equal to, now this is on the basis of the shear stress, right? Shear failure of the thread. So pi DC into H, sigma YT divided by 2 into FOS. Now if we equate this equation A and equation B. So this side, left hand side, it is equal, right? So we can equate this right hand side. So pi DC square into sigma YT, I'll write here sigma YT divided by FOS. This is equal to pi DCH sigma YT divided by 2 times FOS. So sigma YT, this sigma YT will get cancelled. This FS will get cancelled. Anything is there? Pi, this pi, okay. 1 DC from here and 1 DC from here. What will remain here? Now here it is 2. This is 4, so this will become 2. So H, it is equal to DC divided by 2, right? Or H, it is equal to 0.5 times the DC. What is the meaning of this? If what was our assumption? That there should not be the failure of the threads in the nut, but the failure occurs in the threads of the bolt only, right? This was our assumption. Now see, if you want the threads should not get fail in the bolt, in the nut, then height of the nut minimum should be 0.5 times the DC. Okay. Now, assume that this DC core diameter, it is equal to 0.8 times D. Okay. I'll tell you why. Because approximately every time we are getting whatever the pitch and all, DC is equal to 0.8 times D, or D it is equal to 1.19 times the DC, means 20% more. It's 1.19. Okay, approximately it is 19 to 20% more. So if DC is equal to 0.8 times D, if I substitute here 0.8 times D, then I'll get H it is equal to 0.4 times D. Means at least the height of the nut should be equal to 0.4 times the nominal diameter. You know what is the height of the nut? In standard, whenever we are purchasing any nut, hexagonal nut in the market, then this height, see here, generally this nut is having a hole, right? If I draw here the top view of this, now there is an internal threads, so this is 3/4. Now this diameter D, always this height, it is in terms of D, and this height, it is represent in a thickness T, and this thickness T, it is equal to 0.8 times D to D. That means T is equal to D, or so this in this range, right? So thickness it is equal to 0.8 times D to D. Means, what is the meaning of this? See, minimum you require, the height of the nut is 0.4 times D. If the height of the nut is less than this, what will happen? The threads of the nut will get failed, right? It will get sheared off, and your whatever the joint it is there, that will fail. So therefore, see, here it is written for the standard coarse threads, the threads are equally strong in failure by shear and failure by tension if the height of the nut is approximately 4 times the nominal diameter. But in general practice, see, the height of the standard hexagonal nut, it is 0.8 D, and hence the thread of the bolt in the standard nut will not fail by shear. You understood this? The thread of the bolt will not fail by the shear, because we are taking the height of the nut, it is more than 0.4 times the D. Okay, so we design the nut and bolt in such a way that it should not get sheared off, right? So as I told you, this line is saying that only the correct size of the bolt. What is the design of bolt? Design of bolt means you have to find out the nominal diameter, right? And the pitch. Now, in metric screw threads, this DC core diameter, this is equal to nominal diameter minus 1.2268 times the pitch. But again, this pitch is unknown. And suppose this D is also unknown, and you know only this DC, then it is difficult to convert this into the nominal diameter, right? The pitch is different again. And therefore, the general relationship, or you can say the approximate relationship, it is core diameter, it is equal to 0.8 times D, or as I told you, the nominal diameter, it is equal to 1.19 times the DC. Or even this is actually, it is not 1.19 only, it is 1957. So approximately it becomes 1.2. And so it is reverse. You can say DC is equal to 0.8 times D, or D is equal to 1.2 times DC, right? 20% less or 20% more. Okay, so whenever generally when we design it, always, as I told you, the weakest section of the bolt, it is core diameter. So when you are doing the calculation, during calculation always you are getting DC, and once you get DC, you have to convert that core diameter into the nominal diameter, and when you want to convert this core diameter into the nominal diameter, always use this relation. D it is equal to 1.9 times DC, or maximum up to 1.2 times the DC. Okay. Okay, you understood this, because you have to use this part in the further principles.
Yes, sir.
Okay. Now, there is one more principle, and that is called the uniform strength. Now, what do you mean by the uniform strength? Generally, if you see this bolt, now see here, whatever this short line, it is shown up to here and up to here. So this diameter, it is the core diameter, right? Now suppose you are tightening this and there is a tensile force is acting inside, and then due to that the tensile stress is developed. Now this tensile stress, see here it is, there is no threading. That means threaded portion is up to here only, right? And up to this portion, what is the minimum cross-sectional area of this threaded portion? It is the core diameter, right? Which is DC. And here, what is the diameter? Here it is D. Now that means what? Here, the sectional area, cross-sectional area, it is more than the cross-sectional area here. Now, if the cross-sectional area is less here in this threaded portion, then definitely the trace is more, right? The stress is more in the threaded portion than this cylindrical portion. So that means the trace is not uniform. If the stress is not uniform, definitely the strength of the bolt is not uniform. This bolt, I can say reverse, that in this portion, in this cylindrical portion, the strength is more, right? Than this threaded portion, the strength is less. Correct? So this is not the uniform strength. This bolt is not having the uniform strength, and which is not required in general application. I am saying which is not required in general application. But there are certain applications where on that bolt some fatigue load is acting, some dynamic load is acting. In that case, the strength of the bolt should be uniform, right? So how to convert this non-uniform strength bolt into the uniform strength bolt? See, if you read this in ordinary bolt, the cross-sectional area is minimum in threaded portion. In other words, the stress in the threaded portion of the bolt will be higher than that in the shank. Shank means this cylindrical part. Okay. If now, how to reduce this, how to make it uniform, what I can do here, when it will become uniform, when the cross-sectional area is same, right? When the cross-sectional area is same, in that case, you can say the bolt is having the uniform strength. Now, what we can do here, one possible thing is, whatever this cylindrical part, the diameter instead of D, we can take BC. So this is minimum diameter. Here also you will get the minimum diameter. So the strength of the bolt will be uniform. Correct? That is one way. Here it is shown in the red line. The shank diameter is reduced to core diameter. The stress becomes same throughout the length of the bolt, and hence the impact energy is distributed. What I told, whenever there is a dynamic load acting on the bolt, especially in the IC engines, the engine is running at high speed and there is a reciprocating motion. Due to that, a high dynamic load is acting on the bolt whenever we are fixing the cylinder head to the cylinder. There we are using the bolts. So that bolt is having the dynamic load, and in that application, most of the time we require the uniform strength bolt. So for making the uniform strength, instead of this nominal diameter, we'll use here the core diameter, right? So that the strength is uniform throughout the bolt. There is another alternative for this. You can keep this diameter D only, but at the center you can make a hole, and this hole is in this cylindrical portion up to here. Okay. Now what should be the diameter of this hole? Now you have to drill a hole here such that the cross-sectional area here and here must be same. Now suppose here if this is B1, right? This diameter, the hole which you have to drill here, right? This B1, it is equal to how much? Will you calculate this? Can anyone tell me how to make the cross-sectional area uniform? See, when it will become uniform, when the cross-sectional area here at this section and here at this section is same. Now in the threaded portion, what is the cross-sectional area? Pi by 4 DC square. This is equal to the cross-sectional area. Now if I cut here and if I draw here that cross-sectional area, see, suppose this diameter is D and at the center there is a small hole of diameter is D1. So what is the cross-sectional area? Pi by 4 D square minus D1 square. This will get cancelled. So DC square, I'll write here, equal to D square minus d1 square. So can I write d1 square? It is equal to d1 if I take on this side, sorry, d square minus dc square, and therefore d1 it is equal to under root of d square minus dc square. Right? This okay? So I know here this diameter, I know the core diameter also. You substitute here under root of d square minus dc square, you will get the value of the d1, right? And then take that value and drill here that hole throughout in the shank up to this, then definitely the strength of this part and strength of this threaded portion part will become same, and it will become the uniform strength bolt, so that it will take a dynamic load. Okay? Hello?
Sir, won't there be stress concentration at the second at figure B in where the fillet is there?
Which fillet you are talking about?
Sir, in figure B, when we
Ah,
reduce the shank diameter,
right, right,
so
right.
there is a fillet
Definitely.
kind of a thing.
Yeah. Definitely there will be a stress concentration, but that stress concentration will not be a functional one. I will remove this. Uh, you are talking about this portion, right?
Yes, sir.
If I'm not wrong, right? See, why that is not important here? This is my diameter, right? And here this is the threaded portion. Okay, and I'm saying that this is my DC. Always the stress concentration will apply over the minimum diameter. Okay, now this diameter, it is bigger than this. See, your minimum cross section is at this DC. Okay, and this is above that. So whatever the load is acting here, this tensile load will act always, it will affect on the minimum diameter and not on the more than that. See here this portion, because here again this threaded portion is something like this. Okay, but throughout this threaded portion, the minimum area is DC, and which will coincide with this DC also. Okay, so this part is slightly on the upper side. Now see, if suppose if I consider a small hole here in this shank, this diameter of this hole is very small. Suppose I'll say D2, but now this will affect more than this. So this is outside. This is outer part. This will not affect because here the stress is acting at the minimum. Here it is the most stress than this. Whereas now here, if it is, even if you take small hole, this one, now the whole weaker section is not now this one. My weaker section is here, and the stress now, see the stress lines are generally like this if it is uniform. Okay, but if you have a small hole here, Now the stress lines will become this way. So I'll draw a enlarged one like this, and this line is like something like this. So whatever the lines passing through this area, it will concentrate here, and the stress is more here because the cross-sectional area is less. Right? If you drill a 1 mm hole or 1.5 mm hole, the chances of the failure is here at this hole only. Okay, but stress concentration will not affect here because that is the outer part. You understood?
Yes, sir.
Whereas in the third case, there is a question of stress concentration, and that's why here the strength will reduce. See here along this is the hole. Here it is wrongly shown actually up to here, but this hole should be up to this one. Okay. Now, as we are removing the material, definitely that's not our aim. We are reducing the strength of this shank, right? And how much that strength we are reducing? We are making equal to this strength where there is a core diameter, right? And how? By making this hole. Okay, so definitely here the stress concentration is more, and that's why the strength will be less, and that's what we require. We want the strength of this portion and strength of this portion is same so that it will become uniform. Okay.
Yes, sir. Thank you.
Sir, in the second case again, would there be shear failure again because DC and at the junction, like where she
Yeah,
said there's
yeah.
a fillet, there
Yes,
would
yes,
be
yes.
shear happening,
Shear,
right?
shear will happen, but that's what means. That's why here I conclude that if the height of the nut, if it is more than 0.4 times D, then we can avoid the shear, right? Otherwise, definitely the shear will occur. Means chances of failure is one is the tensile failure and another one is the shear failure of the threads. That is always there. Wherever there is a threads, always the one possibility of the failure is the shear failure of the threads. That's why sometimes if suppose the load is very high, which will be more than the design load, then the slipping will occur. Whenever we are taking a small screw and nut, you observe that you just apply with the help of some holder or screwdriver. If you apply very high force, what will happen? That threads will get slipped, right? Because that height, that whatever the depth of the thread it is there, it is very small. So definitely there is a chances of, because we are applying the very high load and that nut or screw is not designed for that much load. Okay. And that's why you have to operate the very carefully, the small part. Now, when it is a big part, so definitely we are not using there the manual force. We use the different machines for even for tightening the nowadays for tightening. You must have seen even in the automobile garage and all, they are using some machines for fixing the nut. Just they are holding the nut and then they press the button, it will rotate speedily and that nut will get fixed there. So you have to design the devices in such a way that whatever the torque we are applying, that torque should not go beyond the design limit. Otherwise, definitely either your bolt will fail or your nut will fail. Correct? So whatever the design force, now here you can see this P, whatever P we are saying here, this P is crucial. No? For this value of P, you have decided DC. Now suppose just take an example of, suppose if I say here the P it is equal to 40 Newton. So for this P, you calculated DC, right? Now, instead of, suppose my DC is, core diameter is 10 mm. Okay. Now, whenever you are applying this 40 Newton up to this load, this will work. Now, instead of this 40 Newton, if you apply 80 Newton, right? Now, okay, you have taken FOS, right? Factor of safety. But definitely that factor of safety, it is up to certain limit. If your load is suppose 1000 Newton, you are applying the 1000 Newton instead of 40 Newton. Your design load is only 40 Newton and you are applying the 1000 Newton. Definitely your bolt or nut will fail, right? It will not sustain. So that's why always this design, it is up to the certain limit. And then in that case, the failure can occur. It is, one is the tensile failure and another one is the shear failure of the threads. Okay. And that's why wherever there is a, just take an example of your screw jack. Suppose somewhere on the highway, truck fails and this truck is loaded with very high load, 50 tons or maybe 100 tons load, and he wants to change that tire. So definitely he has to use the screw jack. Now with the help of that screw jack, he has to lift that 100 tons load. Now if your screw jack is not designed for that much load, it will not work. It will fail, right? So whatever the part you are using for your application, so you have to see first whether it is designed for that much load. If it is not, you can't use. If it is designed for that much load, then only you can do that. That means if the load is high, it will fail. So same thing here also can happen. But whenever if someone asks you that which type of failure can occur in the belt, so always there are bolt. There are two types of failure. One is the tensile failure and another one is the shear failure of that means shearing off of the threads. Okay. Right. Now.
Yes, sir.
With this, now here the most important part, that is draw here. There are three types of eccentric loading acting on the bolt joint. Eccentric load. Now, you must have seen even at your home also, some this type of bracket is there. You have a bracket, right? And you want to keep some things over here, correct? And this part, this you have to fix to the wall. Okay, I drawn here one view. In another view, this looks something like this. If you understand the drawing. This way. Now, here I am using some bolt. Okay, suppose one bolt is here and here also another bolt, and here also I am using one more bolt. Correct. Now this bolt is like this here. These are the bolts. Now, yes, 3 bolts are there. We are fixing this to the wall. Okay, this wall is there. Suppose in industry, we have to keep the number of tools here which are heavily loaded, right? And we don't want to put on the ground level at certain height so that that operator can easily pick up that tool. He will not able to bend and all these things. So at that particular height, we want to keep this. So definitely we have to use here some bolts and something like that, and we have to fix it. Suppose we are using here this bolt, and this total load I'll consider here, whatever this load is, this P. Now, when it will fail and how it will fail, tell me. This load is acting here, okay? This is suppose P, and I'm using here this bolts for fixing this frame to the wall. वन चांस जनरली घर में होता है अपने कि ये जो भी स्क्रू या बोल्ट जो भी लगाते हैं अपन वो निकल आता है, राइट? इफ द होल साइज गेट्स मोर than the size of the screw, correct? जो भी whatever the screw, and this is suppose head. So this is happening that completely screw या bolt निकल आएगा. That is one failure, but it is not a failure of this bolt, correct? Now, if the force is acting here and the bolt is like this, that means which type of failure can occur here?
So could you repeat the question?
These are the bolts, okay? Bolts are like this. I'll draw here separately. This is my one bolt, this is another bolt, and the load is acting here. Now, one failure is I can consider this actually the eccentric bolt, right? Eccentric load. It is acting away. But if I consider suppose some portion of the load will act here only, right? So here the shearing can occur, correct? If this is my bolt, so shearing can occur here. यहाँ से ये shear हो सकता है और एक टूट जाएगा, correct है? So direct shear can occur. And another one, because of this eccentricity, this may get extend or elongate, and that is due to the tensile force. Is it?
Yes, sir.
Right? So,
Sir, this sorry, sir. Sir, this topic is a little difficult to understand, and now we have a lecture. So, is it possible to conduct this next time from the beginning?
I will. Okay. I'll
you,
take
sir.
once again. All right.
Thank you, sir.
Okay, I think already it is 2:10, no? Okay, 2:13. Okay, we'll discuss this tomorrow. I think tomorrow you have, I don't know. If it is tomorrow we'll continue this. Okay.
Thank you, sir.